So when we look at the most fundamental particles in the universe, we see that there are 6 particles called quarks that make up much of the matter: protons, neutrons, baryons, hadrons, those types of particles. The 6 types of quarks are the top and bottom, up, down, strange, and charmed quarks. And each of these quarks has an anti-quark, the anti-top, the anti-bottom, and so on. There are also 6 leptons. These leptons are also fundamental particles. They cannot be broken up into smaller particles. Like quarks, they're fundamental. There's the electron, which we're all familiar with, and there's an electron neutrino. There's a muon and the muon neutrino, the tau and the tau neutrino. Those 6 particles also have antiparticle companions. There's the positron, is a unique name for the antimatter electron. There's the antimatter electron neutrino, the antimuon, the antimuon neutrino, and so on. So really there are 12 fundamental particles and 12 antiparticles that basically make up what we see in the universe. Mesons, which we talked about before, mesons when they decay into leptons. Mesons are composed of 2 quarks, like an up and a down or an up and a bottom or something along those lines. And baryons can have 3 quarks. For example, 2 very famous baryons that we're all familiar with: the proton. The proton has an up, up, and down quark. Neutrons have up, down, and down quarks. Well, how does the charge work? Remember, the proton has the same charge as an electron, equal and opposite. It has a charge of plus E, and the electron has a charge of minus E, or 1.602 times 10 to the minus 19 coulombs. Well, if a proton is broken up into 3 different quarks, how does it have a charge of plus 1? Well, it turns out each of these quarks has a charge. The up charge has a charge of plus 2/3. This up has a 2/3. So positive 2/3 plus positive 2/3, and the down quark is minus 1/3 charge. So when you add these charges together, 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3, 3/3 is equal to 1. The proton has a charge of 1. But when we do for the neutron, we have 2/3 for the up quark, minus 1/3, right? Because it's negative 1/3 for the down quark, minus 1/3 for the second down quark. 2/3 minus 1/3 minus 1/3 is equal to 0. The neutron has no charge. So even though the neutron has no charge, the particles inside it do, but they add together to form a neutral particle. Just like a hydrogen atom, it has 1 positive proton, 1 negative electron. From a distance, it looks electrically neutral. Now, quarks can change flavor via the nuclear weak force. This is what happens when you have proton decay. When a proton becomes a neutron or a neutron becomes a proton, what you get from beta decay. What's really happening is that the proton becoming a neutron, when a proton becomes a neutron, one of the up quarks becomes a down quark. Or for the neutron becoming a proton, one of the down quarks becomes an up quark. That change takes place because of the nuclear weak force. The nuclear strong force cannot change the flavors of quarks. The things that hold the protons and neutrons together in the nucleus cannot change the flavor of a quark. Now, quarks also have an additional property. Again, we're talking about all these strange properties these particles have. But quarks have a property called color. Think of it like charge, right? Charge is arbitrary, positive, negative. That's just an arbitrary designation that Benjamin Franklin gave, talking about 2 different, you could have called it north and south, like we did with magnets. You could have called it east and west, up and down, whatever. Quarks have a property called color, where quarks actually have 3 different flavors. They're called quark flavors. They can be red, blue, or green. Now, flavor implies you taste a quark, and of course you can't. It's just a designation given to quarks. Quarks combine. A quark cannot exist on its own. A quark can't, you don't have quarks floating in space on their own. They have to be together with other quarks in such a way that they are color neutral or white. So a red, blue, and a green quark, so if one of these is red, one of these is blue, one of these is green, can combine to form a white proton. Now, if you look at the additive light in an RGB monitor, red, blue, green monitor, if you add red light to blue light to green light, you do get white light. Another way to get white light is to combine a color and the anti-particle with that color. So combining a red and an anti-red also gives you a white color. So this theory, quark theory, including colors or flavors of these quarks, is called quantum chromodynamics. Quantum because, of course, it's studying the very small. Dynamics because it's talking about how these particles interact with one another. Chromo meaning color. So the distinction of how particles interact with each other deals with quantum chromodynamics. Now, the physics gets pretty complex, right? All these different particles, all these different names and classifications we have to worry about. But in the end, what is the actual goal of a physicist? It's to find the underlying structure in the universe. So we'll talk in the next video about the tasks that physicists are doing to try to simplify this zoo of particles.